Project Granite, an exercise in alien biospheres, the 6th episode by Burma 118. In the first part, we discussed Yerkes classes 1 to 4. In the second part, we discussed within Yerkes class 5, Harvard class O to A. In the third part, in Yerkes class 5, we then discussed Harvard classes F to M. And in the fourth part, we'll discuss Yerkes class 6, within Yerkes class 5, the Harvard class L to Y, and stellar remnants. So we'll be discussing subdwarves, brown dwarves, and stellar remnants, which include white dwarves, neutron stars, and black holes. So, subdwarves. Subdwarves are type 6, as we discussed previously. Cool subdwarves, whose spectral type range from G to M, and brown dwarves, are smaller and less bright than population 1 stars of the same temperature. Since they have lower metallicity, this decreases opacity, which decreases the radiation pressure, causing the stars to be smaller. Because they have less area to radiate through, they're 2 times dimmer than stars of the same temperature. They're also more bright in UV because they're less quote-unquote metals to absorb it, and because they're hotter, but not hot enough to counter the decrease in luminosity. Hot subdwarfs, however, form through different channels. B-type subdwarfs often form due to interactions with the binary partner, ripping off the outer hydrogen layer before helium starts to fuse. So the subdwarfs just chill and then become white dwarfs. SDO stars can also be formed through interactions with the partner, but they more often form due to fusion between 2 white dwarfs. In the inside of hot subdwarf star, there's a thin layer of hydrogen, a thick layer of helium, and a carbon and oxygen core. Now for brown dwarfs. Brown dwarfs have 3 spectral classes: L-type, T-type, and Y-type. L-type stars have a temperature more than 1300 Kelvin and are able to do simple hydrogen fusion. T-type stars have a temperature above 500 Kelvin, and Y-type stars have a temperature less than 500 Kelvin. L-type stars have a deep red color, T-type stars have a color magenta with some bands, and Y-type stars are dark purple with bands. Brown dwarfs are about the radius of Jupiter, regardless of their mass, and in brown dwarfs, their clouds, from the lowest to highest clouds, are perovskite corundum, liquid iron, and forsterite and enstatite, with carbon monoxide throughout for L-type stars. The previous clouds, along with sodium sulfide, lithium sulfide, and lithium fluoride and potassium chloride for T-type stars, but with carbon monoxide near the bottom and methane near the top. And for Y-type stars, the previous, in addition to rubidium chloride, cesium chloride, water, ammonium hydrosulfide, ammonia, and other gases that condense at colder temperatures, with a similar distribution of carbon monoxide and methane. However, it's still mostly hydrogen and helium. Here's the cooling curves. They gradually cool. However, more massive brown dwarfs cool slower. And here's the structure of a Y-type star. And as you can see, the belts are formed by convection currents and the Coriolis effect. Stellar remnants. White dwarfs are also known as spectral class 7. Their temperature can range from 150,000 Kelvin to 4,000 Kelvin. Their solar mass can vary depending on their formation method. White dwarfs between 0.17 to 0.75 solar masses can be formed by a binary partner stripping hydrogen off a medium mass star. 0.5 to 1.05 solar mass white dwarf can be a carbon-oxygen white dwarf from a 0.5 to 8 solar mass star. A 1.05 to 1.44 solar mass white dwarf can be oxygen neon magnesium white dwarf from an 8 to 10 solar mass star. White dwarfs of various masses up to 1.44 solar masses can be a carbon-oxygen white dwarf from the fusion of 2 white dwarfs. And white dwarfs from 0.08 to 0.5 solar masses have not formed that aren't a result of gas stripping yet, but after a long time they will form, and they will be helium. They are less than 0.02 solar radii, as shown by this curve. The higher the mass, the lower the radius. Their luminosity in solar luminosities ranges from 1/10,000th to 1/100th of a solar luminosity. Their lifespan is trillions of years, and they're 10% of star mass objects currently, but 97% of stars will become white dwarfs. White dwarf novae occur when a white dwarf accretes matter from a partner, and it fuses and creates a flash. A type Ia supernova happens when a white dwarf gains enough mass to go above the 1.44 solar mass threshold, causing the carbon to fuse and causing a carbon flash that blows it up. Okay, neutron stars and black holes. Up here is a graph which shows the different kinds of stellar remnants that can form. As you can see, if the solar masses is more than 10, and at any metallicity, if it's less than 25, or if it's high enough metallicity, neutron stars can form. Otherwise, if it's less than 10, it's white dwarfs, and otherwise, if it's more than 25 solar masses and low enough metallicity, black holes can form. The bottom graph shows methods of supernovae. If the solar masses are less than 25, then and the metallicity is low enough, then a supernovae, which is type 2p, can occur, where hydrogen remains and it gets ionized by a shock and becomes opaque, causing a temporary light plateau. The green, which is a small sliver, represents supernovae type 2l, which has not much of a hydrogen envelope, but still has it, resulting in no light plateau. If it's more than 25 solar masses and the metallicity is high enough, like not very high, just like above like -1, then a supernova type 1b can occur, where no hydrogen remains because it's all blown off, and some to little helium remains due to sheer mass of the star. And red represents a pair instability supernovae, where the star explodes in such a way that nothing's left behind. So neutron stars are formed when a stellar remnant more than 1.44 solar masses but less than 3 collapses enough to become a ball of neutrons. Neutron stars are about 10 kilometers in radius. Some neutron stars spin so rapidly that they emit radiation through their poles, and those are called pulsars. Black holes are formed when the stellar remnant is more than 3 solar masses. A black hole's radius is directly proportional to its mass. So the minimum radius is 9 solar radii. Ignore what I wrote. They form because the gravity of the remnant is stronger than the forces holding the neutrons apart. And some important locations of black hole are the ergosphere, where it's impossible to remain stationary relative to outside frame of reference, the event horizon, where light cannot escape, and the ring singularity. They also often have a hot accretion disk, especially when they have a partner to accrete matter from. So verdict. All of these suck. Brown dwarfs and white dwarfs suck because they become too cold too quickly for habitable plants and would exert large tidal forces that release greenhouse gases. Subdwarfs suck because they have too little metallicity to form planets, and neutron stars and black holes emit too much radiation for habitability, at least for Earth-like planets. Let your imagination free if you don't wish to have Earth-like life.